We find our irreps by constructing left ideals in the group algebra, and we get these left ideals by right multiplication with primitive idempotents. And these primitive idempotents, they are linear combinations of the group elements with, in general, complex coefficients. And now these complex coefficients, they encode all the information on the irrep, and it's actually possible to explicitly calculate the characters in terms of these coefficients. So here we see the complex conjugate of the coefficients. We sum, if we want to calculate the character of group element H, we sum over all groups in the same conjugacy class as H, and then there's some normalizing prefactor involving the order of the group and the size of the conjugacy class. Before we prove this, let's remark that if we know the characters, then in particular we know the dimension of the irrep, because the dimension of the irrep, that's just the character of the identity. And if we look at this formula here, in the case of the identity, the sum has just one term because the identity is a conjugacy class of its own. So this NC here is 1. We just get the order of the group and then the coefficient of the identity complex conjugated. In order to prove this theorem, we define a linear map, let's call it A sub H, from the group algebra to the group algebra, that maps an element of the group algebra R to H inverse R E mu. And now what we're going to do is we're going to calculate the trace of this linear map in two different ways, using two different bases, and by comparing the results we will establish this identity here. So first, let's calculate. First we're going to show that the trace of A is just the character of H inverse. So this is what we're going to show now. And how do we do this? We use basis for the group algebra. Let's say R1, R2, and so on, until R sub order of the group. So this is a basis for the group algebra. And let's say we chose it such that the first d mu elements, not d mu, R index d mu, these first d mu elements here span such that they are a basis of this L mu, so they span L mu. Now let's apply this H, this A sub H, to one of these basis vectors, let's say to Rj. Then we get H inverse Rj E mu. But since E mu projects to the left ideal L mu, this expression is 0 whenever the J is larger, equal to, larger than d mu. Then it's 0. So we can now restrict our attention to the case that J is less than or equal to d mu. And what do we get then? AH applied to Rj, that's H inverse Rj. And now the E mu here, we don't have to write this, because the E mu does nothing on the first d mu of these vectors here. Just leave them invariant. So we get what? We get sum here, a linear combination of the first few of these vectors, just these here, and the coefficients are just the matrix elements of our irrep. So let's say sum k from 1 to d mu rk gamma mu of H inverse, because we're multiplying with H inverse here, matrix element kj. Now, if we want to calculate the trace of A sub H, we are interested in the term where we get the same R as we had here. So we're interested only on the diagonal term. And then we see that we get the character of H inverse in this way. So let's conclude the trace of AH is just sum, let's say j from 1 to d mu. Now here the diagonal elements, jj. And that's just the character of H inverse. And if our representation is unitary, then the character of H inverse is just a complex conjugate of the character of H. But if it's not a unitary representation, then it's equivalent to a unitary representation, since we're speaking about finite groups, and equivalent representations have the same characters, so actually we don't have to assume anything here. This is always true. Okay, so this was the first way to calculate this trace. And now let's use the group elements as a basis for the group algebra, as we often do. So the group elements G are a basis of the group algebra. Now let's calculate the trace in this basis. So first we apply A sub H to G. That's H inverse G E mu. And now we substitute the expression for E mu, which we know. So we get, let's say, a sum over the group elements. Let's call them G prime. Some coefficients here, A sub G prime, and then there's a G prime here, and the H inverse and the G I copy from here. Now for the trace, we are again interested only in the term where here we have the same G as we inserted here. So when is this equal to G? Well, we just solve for the relevant term in the sum for the G prime. So we multiply with H on the left and G inverse on the left. So we find G prime is G inverse H G. That's the term we are interested in. So we can write this as, let's say, A sub G inverse H G times G plus terms that are not proportional to G. Terms not proportional to G. So and if you want to calculate the trace, we have to sum all these here. So now the trace of A sub H, that's just sum of all group elements, and we sum the coefficients A sub G inverse H G. Okay, so what do we sum? What do we get? We get the coefficients for all the elements that are in the same conjugacy class as H, because we are conjugating H with all the group elements. So we get, say, a sum over G prime, and the C here is the conjugacy class of H. Now we can write this, conjugacy class of H, and then it's just A sub G prime. And now how many times do we hit each term in this conjugacy class? Let's look at H itself. How many times do we hit H? Well, that's as many terms as the stabilizer of H, if we consider conjugation as an action, as a group action. So it's just the number of elements of the stabilizer of H. And it's the same for the other terms. Just get the stabilizer here of this element G prime. And now by the orbit stabilizer theorem, we know that the number of elements of the stabilizer, that's the number of elements of the group, divided by the number of elements of the orbit. But the orbit under conjugation is just the number of elements in the conjugacy class, this NC here. So that's where this coefficient here comes from, this prefactor. Now we have only a sum over G prime. No, not all G prime in the group, but only all the G prime in the conjugacy class, and then A sub G prime. Okay, now we can compare. We still have it up here. We calculated the trace here, and once we found the complex conjugate of the character of H, and here we get this term, and if we put these two together, we find this equation here.